Hello, welcome back to the first course in general physics and to part 2 of the study of the mechanics of a rigid body. In this lecture, we will continue talking about the kinematics and kinematical variables of rigid body rotation. And in this context, we will discuss the relation between the linear variables of motion that we have derived for translational motion of a single particle, and between the angular variables that is related to the rotational motion of a rigid body that we developed in the last lecture, in the previous lecture. Then, after developing such relations between the angular and the linear variables, we will use the definitions for the various quantities to redefine these quantities in terms of angular variables. Specifically, we will discuss the kinetic energy of rotation, write it down in terms of angular variables, and we will define in this context the quantity which is the moment of inertia, and we will state one important statement, which is the parallel axis theorem, which allows us to evaluate this quantity, the moment of inertia, relative to any axis of rotation. And then we will move on to discuss the dynamical variables of rotation, the cause of rotation, and in that context we will discuss the quantity torque, which is the dynamical quantity which is responsible for the rotation of a rigid body. So, in the beginning, we will start with talking about the relations between the linear and angular variables of motion. And as we have defined previously, we have defined the linear distance traveled by a particle around a circular path as being the angle theta times the radius of the circular path. And we have to remember that when a rigid body is rotating around a fixed axis, then each point in this body would be executing a circular motion, and thus it will be moving like around a circle, as we have discussed in the context of circular motion of a particle. So the length of the arc that is traveled by the particle, by a given particle in the body, the arc length S is related to the angular displacement theta by S equals theta times R. So this is the position in angular terms, theta, and this is, or the displacement actually, the angular quantity that is traveled in a time, and this is S, the length of the arc that is traveled linearly. That's the distance that the particle travels during that time when it covers the angle theta. And the speed, because here we are not concerned with the vector direction of the velocity, we are concerned with the speed, with the magnitude of the velocity, because we know that the particle is going around a circle, and thus the velocity is always tangential to the circular path. It's always tangential, so we know the direction of it. But what about the quantity? The quantity or the magnitude of that velocity is the speed, and that speed is obtained simply by taking the rate of change of the distance traveled by the particle ds by dt, the rate of change of the distance traveled. And this definitely will give a tangential velocity, because s is the arc length, is a tangential distance, tangential to the arc itself. It's part of the arc. So this quantity ds by dt is thus the tangential velocity, tangential to the arc or to the circular path. And from the previous relation, since the radius of the circular path does not change for the particle, because the particle is at a fixed distance, a given particle is at a fixed distance, and that is the property of the object being rigid, meaning the particles do not move relative to one another in the body. A rigid body, that means once a particle is a given distance from the axis of rotation, it stays at that distance. It does not move far away from it or closer to it. So r is constant. That means ds by dt is simply equals to d theta by dt times r, which is constant. So this way we can derive the linear speed with respect to the angular quantities. And if we compare these two values, to the left-hand side, ds by dt is simply v sub t, which is the tangential velocity of the particle around the circular path. And d theta by dt is simply omega, as we defined it before, is the angular speed of the particle, the rate at which its angular position changes, and r is the distance of the particle from the rotation axis. So this is a relation that we must remember, and we must remember that omega is stated in radian measures. This is very important to remember. Omega in this relation is stated in radian measures because it is derived from the relation S is equal to r theta, in which case theta is measured in radians. So whenever we use this omega and this relation, we will have to make sure that we are using radian measures, not degrees, not revolutions around the circle. Now, if the body is rigid and if it is rotating around a fixed axis, that means omega, the angular speed or the angular velocity in a fixed, will be fixed in space. It will be in a fixed direction because the body is rotating around a fixed axis. So this omega is fixed in direction, and also it is the same for every point in the body. And this is true because the body is rigid, and thus every point in the body, when the body rotates, every point will travel the same angular distance in the same time. That means delta theta by delta t for each point in the body is the same, which means that omega is constant for all the points in the rotating body if the body is rotating with respect to a fixed axis. So this is a statement also to remember in the context of the rotational motion of a rigid body with respect to a fixed axis. However, we have to remember that the body consists of particles that are at different distances from the rotation axis. And since we know the relation between the linear speed and the angular speed, Vt is equal to omega times r, omega being constant for all the particles or the points in the body, that leads to the conclusion that points in the body which are at a greater distance from the rotation axis or having greater radius r, which is the distance of the point, the perpendicular distance of the point from the rotation axis, such points with greater distance from the rotation axis will have greater linear velocity, because the linear velocity depends on omega times r. Omega is constant, r is variable from one point to another with respect to the rotation axis. That's the distance. Thus, v is proportional, linearly proportional to the r distance from the rotation axis of the particular point in the body that we are considering. Now, since omega, the angular speed for every point in the body is constant, that means during the rotation of the rigid body around a fixed axis, if the body rotates with a constant speed omega, with a constant angular speed omega, then we conclude, since omega is the same for all points in the body, then we conclude that each point in the body would execute a uniform circular motion. Each point would execute a uniform circular motion in the sense that each point will be moving as if it were a particle going around a circular path. Thus, we can define the period of revolution or the period of rotation for that point, for a point in the body. The period of rotation is the time taken by the point which is rotating, revolving around the axis of rotation. It's the time taken by the particle to complete one revolution. And that time, which is called the period, can be evaluated. And the time can be evaluated from the linear distance traveled as the particle revolves around a full circle, divided by its speed. If the angular speed is constant omega, that means a particle, as we mentioned, a given particle will be traveling with a constant speed, linear speed, equals omega times r, its distance from the rotation. So it's the velocity or the speed, the magnitude of the velocity for a given particle in the body is constant. It depends on its distance and on omega. The time it takes for a full revolution of that particle is equal to the distance it travels, which is the length of the circular path, which is 2 pi r, divided by the speed of that particle. So the period of rotation is 2 pi r divided by v. Now this period is given in terms of linear variables, simply the linear distance divided by the linear speed. And v here we have to remember that it is the tangential speed. This is the only speed that's available because the particle does not depart, does not change its distance from the axis of rotation. However, in terms of angular variables, we can find this period of rotation because we just developed the relation between the angular variable omega and between the linear variable v, if we substitute instead of v omega r, then the period of rotation or the period of revolution of a particle is equal to 2 pi over omega. Although from the first equation, which is stated in terms of the linear variables, it could be difficult to realize, but looking at the second equation, giving the period as 2 pi over omega, we realize that the period of revolution for any point in the body is exactly the same, which means that each point in the body completes a full revolution during exactly the same period of time. And that is what we mean by the rotation of a rigid body. That's one key point, rigid body around a fixed axis. That is another key point. Now we are ready to look at the acceleration and see how it is related to how do we relate the linear acceleration and the angular acceleration. But we have in the beginning to remember that when the body is revolving around the axis of rotation, the point is each point in it is executing a circular motion. And in the context of circular motion, we know that we have always tangential component of the acceleration, and we have a centripetal component of the acceleration. The tangential component of the acceleration is arising from the change in the magnitude of the tangential speed, while the centripetal acceleration is related to at a given point is related to the magnitude of the tangential speed, as we have discussed previously. So, in a sense, now we will discuss in the most general form, we will discuss the acceleration, the linear and the angular accelerations, and relate them regardless of whether we have a tangential component or not. We always have a centripetal component because the particle is going around a circle. So the centripetal acceleration is always there in this kind of motion. But the question is whether we have a tangential component for the acceleration or not. That depends on the nature of the motion, whether the tangential velocity is changing or not for a given point in the body. But in the most general form, the tangential component is obtained by taking the rate of change of the tangential speed with respect to time. So it's dvt by dt. So in general, this is equal, if we use the relation between vt and omega and r, and remember that vt is equal to omega r is fixed for a given point because the body is rigid and it rotates about a fixed axis. So dv by dt is simply d omega by dt times r. And again, d omega by dt is simply the angular acceleration. D omega by dt is the angular acceleration alpha, and r is the radius of rotation, which is the distance of the particle from the axis of rotation. And this will give us the relation between the linear acceleration, which is the tangential component of the acceleration, because we have derived it from the rate of change of the tangential velocity. A sub t is equal to the angular acceleration alpha times r. And we have to remember that this form of the acceleration gives only the tangential component of the acceleration that is responsible for changing the magnitude of the tangential speed, that is at. And alpha, given in this way, is the angular acceleration, which is responsible for changing the angular speed omega. If alpha is not 0, then we conclude that omega is not constant. It's changing with time. So this is the relation between the tangential acceleration and the angular acceleration. The other acceleration acceleration component that always exists in the circular motion is the well-known centripetal component of the acceleration, which is, as we have discussed before, given by A sub r, in order to indicate that it's radially directed, but it's radially inward towards the center, is equal to v square over r. And again, v here is vt, actually, because the particle is going around a circle, so it has only one component of velocity, which is tangential. So whether we write it v sub t or v, it's the same thing as far as we are considering the circular motion. So this is the same as vt. So alpha ar is equal to v square over r. And we substitute for the value of v using the angular speed instead of the linear speed. Thus, v square is equal to omega square r square divided by r. That will give us omega square r. So the radial acceleration a sub r is given by omega square r in magnitude, and the direction is known to be towards the center. Now we are at a point where we can look into the motion of a rigid body in more details. And we can consider now the problem of evaluating or calculating the kinetic energy of a rotating object. So if we have an object rotating, we will be concerned now in calculating the kinetic energy. Because an object who is rotating, like for example the blade of a saw, when it is rotating, it certainly has a kinetic energy. How can we calculate this kinetic energy for a rotating wheel, for example? The formula that we have so far for the kinetic energy, which is k equals 1/2 mv square, is only applicable to a particle, where we can define a velocity for that particle of mass m. Or at best, we can use this formula for the motion of an object which moves like a single particle, meaning if every point in the object moves in exactly the same way as any other point and as the center of mass. So this is simulating the motion of a single point particle. In that sense, we have the formula, which is k equals 1/2 mv square, which we can apply to calculate the kinetic energy of such a system. However, when we have an extended body that is rotating in space, how can we calculate the kinetic energy? The velocities of the different points in the body are changing as their position from the rotation axis change. The particles in the body are distributed at different distances with respect to the rotation axis, and thus their velocities are different. The velocity of the body is not fixed. The velocity of the different points in the body is not fixed, and thus we cannot assign a specific velocity to the rotation of that body. What shall we use for v, for example? So we cannot do that. We cannot apply it strictly and directly but we can go around this difficulty by simply analyzing the object into particle-like masses. If we divide, mentally at least, hypothetically, if we divide the object, the rotating body, into very small parts, each part is like a particle, very small in size, and having masses m1, m2, m3, and so on. Those are the different parts of the body that we cut it down to. Then, if we evaluate the velocity of that point-like particle, we can apply the definition that we have for the kinetic energy to the motion of that particular point-like particle. We can apply then the definition that we have in hand. Thus, if we divide the object into particles, and we assume that the first particle in the body has mass m1 and velocity v1, the second has mass m2, velocity v2, and so on, we know that the velocities of these different particles are different because these particles are located at different locations with respect to the rotation axis. So we calculate the kinetic energy for each particle, we sum it over all the particles in the body, and then we can get thus the kinetic energy of that rotating object. And the kinetic energy is thus the summation over all the particles of the body of 1/2 mi vi square, where mi is the mass of the ith particle, and v sub I is the velocity, or the magnitude of the velocity of that ith particle as it executes a circular motion. And remember that v here in this formula is the tangential velocity, because every particle in the object is going around a circle, because we have pure rotation in consideration. So this is the kinetic energy. Just instead of having a simple 1/2 mv square, we have summation of 1/2 mi vi square. And we remember that v changes from one particle to another, so we cannot do anything about this summation. But if we use the relation between the velocity, the tangential velocity of the particle, and the angular speed, and realizing that the velocity is given by r times omega, we can substitute that value for v, and we will thus get k is equal to 1/2. It's a constant that we can move outside the summation. Inside the summation, we have mi ri square, and we keep it there. That's in parentheses. And times omega square, and we have removed omega outside the summation because the body is rigid, as we said, and the angular speed of each point in the body is the same as it is for any other point in the body. So omega is fixed for all the particles in the body. So that quantity, omega square, we can move it outside the summation also. So we have this result, which is k equals 1/2 times the quantity in parentheses, which is summation of mi ri square, which depends on the particle I and its location, times omega square. Now, this quantity in parentheses, which is summation of mi ri square, is related to the distribution of particles with respect to the rotation axis. Notice that it is the product of the mass of each particle times the square of its perpendicular distance from the rotation axis. So it is related somehow to the distribution of the particles with respect to the rotation axis. This quantity, in parentheses, we call it the moment of inertia, the rotational inertia of the object, or the moment of inertia of the object. And it is defined as I, the moment of inertia of the object, with respect to the axis of rotation, is equal to the summation of mi Ri square. Notice few features of this quantity. First of all, it depends on the axis of rotation. So I is usually defined with respect to a specific axis of rotation. Since if we change the axis of rotation of the body, then our i's, the distances of the different particles in the body, differ. If we move the axis of rotation, for example, farther from the body, from the initial point, then the distances Ri of the particles are farther away, and that quantity I is larger, or vice versa. If we move that axis of rotation closer and closer to the center of mass, then the distances become closer and closer, and that quantity becomes smaller in magnitude. So essentially, this quantity should be defined with respect to a certain axis of rotation. It's not like the mass. The mass is just the mass of the object. It does not vary with its motion or its rotation. But the moment of inertia does vary with the definition of the axis of rotation, because it does not involve only the mass, it also involves the distribution of mass, how it is distributed relative to the axis of rotation. And also we can realize from this definition that the moment of inertia for a single point-like particle, which means suppose that the body that we are considering that is rotating is simply a single point-like particle. If it is a single point-like particle, then it has a single mass, which is m, its mass, and it has a single distance from the axis of rotation, because it's just one point mass. So it has a distance. If we call it r, then that means the moment of inertia of a single point mass rotating around an axis that is a perpendicular distance r away from it, this moment of inertia is simply equals to m times r square. So m r square is the moment of inertia of a single point-like mass rotating about an axis of rotation that is far away, a distance r far away from that point. So this is just a special case for the application of this formula. And if we substitute this quantity in the definition of the kinetic energy for the rotating object, we get the formula K equals 1/2 I omega square. And this way, if we are concerned with the rotational kinetic energy of an object rotating with respect to a certain axis of rotation, we can evaluate that kinetic energy if we know the center of the axis of rotation with respect to which we can calculate the moment of inertia, or if we are given the moment of inertia directly, and if we know the angular speed of that rotating object, then we can directly calculate its kinetic energy of rotation. And this formula is reminiscent of the formula for the kinetic energy of a translating point-like particle, because in that sense, in that case, k is equal to 1/2 mv square. Here, k is equal to 1/2 I omega square. So all that we have to do is replace the mass in the case of translation by the moment of inertia in the case of rotation, and the velocity v in the case of translation with the angular velocity omega in the case of rotation. So if we replace only the angular velocities, the angular quantities instead of the linear quantities, we get exactly the same form for the kinetic energy. Thus, we have in hand this quantity, which is the moment of inertia, which changes with respect to the axis of rotation, and thus, as we said, it should be determined. It should be specified. It should be specified with respect to the axis with respect to which the body rotates. We have defined this quantity, which is the moment of inertia, with for a system of discretely distributed particles, mi at position ri, m1 at r1, m2 at r2, and so on. Now, what if we want to consider the case of a rigid body which consists of a continuous distribution of matter, meaning there is no boundaries between particle number 1 and particle number 2. The distribution of mass is continuous. In this case, the particles m1, m2, m3 that we divide our body to should have very, very small volumes that is going to 0, and their masses are going to 0. In this limit, the summation mi r sub I square, the summation would be translated into an integration in the usual sense, because we are dealing with a continuous distribution of matter, and then the moment of inertia for a rigid body is defined as the integral of r square dm, where dm is a point, is the mass of a particle around a point in the body, which is a distance r, a perpendicular distance r from the radius of rotation. And remember always that r is the perpendicular distance between the point we are considering and between the axis of rotation. So this integral r squared dm integrated over all the body gives the moment of inertia of this body. Now, let's move to a theorem that allows us to calculate the moment of inertia for a body with respect to a general axis. We have mentioned that the moment of inertia changes with the axis of rotation. It's not a fixed quantity. So what do we do if we have an object that can be rotating around any axis in space, which could be an infinitely large number of axes that we can select? So it is impossible to define a specific moment of inertia for the body. However, we can always define a specific moment of inertia for the body and depend on that moment of inertia to determine the moment of inertia with respect to any other axis. That moment of inertia is the moment of inertia of the body with respect to axis of rotation going through its center of mass, because the center of mass of the body does not change. So if we define our axis that it's the axis of rotation, that it's an axis that goes through the center of mass in a certain way, and we calculate the moment of inertia with respect to this axis, and we call it I sub cm, meaning the moment of inertia with respect to an axis of rotation through the center of mass. If we call it I sub cm, then I sub cm with a certain orientation of the axis is fixed. For example, if we have a spherical shape, a sphere, then any axis through the center of the sphere would give exactly the same moment of inertia ICM. So it's the same for a sphere. However, if we have a disk, if the axis of rotation is perpendicular to the plane of the disk, then we have a given ICM, ICM1, for example. And if we have the axis of rotation that goes through the center of mass, but it is in plane, then the disk rotates like this rather than this, then this will give another value for the moment of inertia, which is a second value, let's call it ICM2, for example, for an in-plane. But at any rate, ICM1 is constant. It does not change with the motion of the object. And ICM2, it does not change with the motion of the object. And we can use these values, ICM, and use it to evaluate the moment of inertia with respect to any axis of rotation by using the so-called the parallel axis theorem. And that parallel axis theorem states that if we have an axis going through the center of mass, and the moment of inertia with respect to that axis of rotation is ICM, then we can evaluate the moment of inertia of the body. In this example, it's a disk rotating. We can evaluate the moment of inertia of that object with respect to any other axis that is parallel to that axis going through the center of mass, if these two axes are parallel, and if they are a distance h apart, where h is the perpendicular distance between the two axes, then the moment of inertia with respect to the new axis is equal to the moment of inertia with respect to the axis going through the center of mass times mh square, where capital M is the mass of the object, rotating object, and h is the distance between the two parallel axes. So this way, if we know the axis, the axis of rotation, how far away it is from the axis through the center of mass, and we know the moment of inertia with respect to an axis going through the center of mass, then we can determine the moment of inertia with respect to the new axis. And now we are at a point where we can discuss the dynamical variables, and we know that if we apply a force on an object, the force will cause the object to move. In the general sense, the object moves in two ways under the influence of a force, an external force. It could move in a translational manner, as we have discussed previously with translational motion. It could also move in a rotational manner, as we might notice if we push a ruler from one end with a force, then the center of mass of the ruler translates. At the same time, the ruler will be rotating as its center translates. So in general, we have a translational motion and a rotational motion, and that the rotational motion arises due to the influence of a dynamical quantity which we call the torque, and this torque is resembling the force in the context of the translational motion. This torque is the quantity that generates the rotation, and we will be discussing the effect of such a dynamical quantity in the next lecture. And now I will stop this lecture and thank you for your attention.